Okay, Assalamualaikum. Today I'm going to continue on example 2.9. The last class we stopped at VSPU equals to 1.051. Okay, so this value is actually for a single phase. Okay, so the question actually want us to calculate. Okay, so if you remember, the question want us to calculate the VS actual. Okay, 1 per phase. And another one is for line to line. Okay, all right. So do you still remember the formula of VPU equals to V actual divided by V base? And also another formula, okay, V phase equals to V line to line divided by square root of 3. Okay, so this formula, okay, and another formula of this is very important, okay, to remember. Okay, so next, okay, when we want to calculate the VS actual, okay, we reshuffle this formula. Okay, so that will be VPU times V base. Okay, so VPU we already calculated that as 1.051. Okay, times by V base. Okay, so if you remember, we are given the V base as VLL 4,400 volt, yeah. So this is given in the question. Okay, so but this is VLL. So what we are calculating here is per phase. So we use the formula, this formula. Okay, we're going to apply it here. So that will be 4,400 divided by square root of 3. And then you get that as 2670 volt. So this value is actually VS actual for single phase. Okay. Alright, so next we want to calculate the VS actual for line to line. Okay, so again we're going to apply the same formula, VPU times V base. So VPU is 1.051 times V base. Okay, because this time is VLL. Okay, so we're going to take straight. That will be 4.62 kV. Okay, so that's for example 2.9. So next we're going to move to the summary. So in this summary, okay, all I want to stress is the exercise. Okay, so in order for you to understand per unit, you have to do all the examples that we have been working with together. Okay, and then memorize all the equations that I say that is important. Okay, so if you can manage to do all the examples that we did in the class, you will have no problem with the per unit. Okay, so changing the base of per unit quantities. Sometimes the per unit impedance of a component of a system is expressed in a base other than the one that selected. Okay, so sometimes you have a machine. Okay, so the machine has first, okay, selection 1. So you design a machine and then you have a criteria of the machine. Okay, you know what is the power is, and then you know what's the voltage and also the impedance. So you design, okay, your machine to be this much voltage, this much power, and has this much impedance. Okay, and suddenly, okay, someone else bought your machine or want to upgrade the machine. Okay, all right, so if they want to upgrade the machine will now, okay, have a different value. Okay, so you want to have a bigger voltage, okay, and then of course they want to change the power. Okay, all right. So they changed. So we have to change the voltage, and also, of course, we have to change the impedance. Okay, so this is the example where now we have to change the base, okay, of the per unit quantities using this formula. So if you see here, this formula is important, okay, where it shows you, okay, the first selections, okay, the first one that we designed the machine. Okay, now we want, okay, to change the value of the power, the V, and also the Z, okay, according to the new value. Okay, so when this happens, you have to apply this formula. Okay, and you have to know this formula and memorize this formula. Okay, you will see it's quite straightforward question. Okay, for example, question 2.1. If you see here, okay, this question is very straightforward if you remember the formula. Okay, so in this question, you have a generator, okay, designed as X, okay, is given as 0.25 pu, okay, so that is the reactance. Because why? Because the question hints you the reactance as 0.25, so automatically you know that that is your ZPU. Okay, so that is the old one, of course. Okay, based on generator nameplate. Okay, so this is the first design of your generator, so means that this is your V base old. Yeah, because this is what original. Okay, all right, so next, okay, is 500 mega, so this of course is your S base old. So this is the original value of the generator, okay, before you want to, okay, increase the voltage, all right, because before you want to decrease the S, okay, so you want to design this, so this is your new value. All right, so if you see here, everything is very straightforward. You know each of these, okay, based on the question, so you just have to put everything inside the formula and you get the new value of the ZPU. Okay, all right, so next we're moving on to one line diagram. Okay, one line diagram is also known as a single line diagram. So this is a simplified notation, okay, based on a three-phase system. Okay, in this part, in the single line diagram, everything is represented in the block diagram. Okay, so this block diagram will actually shows you the path of a power flow, okay, between the entities of the system. Okay, the entities of the system can be the circuit breaker, the transformer, capacitor. Okay, so everything is based on the schematic symbols. So we're going to see the symbols. Okay, so these symbols are very important. You have to know. Okay, all right. One that you look very familiar is of course the transformer, and also the ammeter and the voltmeter look very familiar. And the rest you have to know. Okay, the circuit breaker looks like a square, and then the round is a machine. Okay, it's very important for you to be very familiar with the symbols. Okay, for example, in this, okay, you have this is per phase, okay, impedance diagram. Okay, all right, so we want to convert this per phase into single line diagram. Okay, if you see here, it's the same. Okay, we still have two source. We have source 1, source 2. Okay, we have load A and we have a load A here. Okay, we have a transformer. Okay, the square here is actually the circuit breaker. All right. Okay, so you can see that, okay, this diagram is actually the same as the single line diagram. Okay, so that's all for chapter 2.